and welcome to another WJEC A level physics question. This time it's question 7 from Unit 1, May 2017, and it's a particle physics question. It's a short question because it's only a QER, so it's 6 marks, but there's lots of detail we can put into this question. So what we got is the decay of a neutron given in a formula, and we've got to give a detailed description of the process, including how conservation laws apply. So what I'm going to do first of all is I'm just going to simply state what's happening here. This is actually a beta decay. So there we go. So this is beta decay, where a neutron in this case. Oh, let's write down the right word. So the neutron decays to become a proton, an electron, and an electron antineutrino. Now it mentions that we're going to use conservation laws, and apart from sort of conservation of energy and conservation of momentum, when we apply particle physics, we apply conservation of charge. So let's look at that. So on the left hand side of the equation, the total charge is 0 because we just have a neutron. On the right hand side of the equation we have a proton which has a charge of 1e, or 1 compared to the electron charge of 1.6 times 10 to the minus 19 coulombs. The electron has a charge of minus 1e, and the electron neutrino is neutral. So we've got a total of 0 charge on the left and a total of 0 on the right. We can also apply conservation of baryon number. On the left hand side, a neutron is a baryon. On the right hand side, a proton is a baryon. An electron isn't, and nor is the electron antineutrino. Remember that baryons are particles made up of 3 quarks. So we've got a total baryon number of 1 on both sides of the equation. We can also apply conservation of lepton number. On the left hand side we have 0 because the neutron is made of quarks and leptons aren't made of quarks. On the right hand side the proton, similarly to the neutron, is 0. The electron has a lepton number of +1 and the antineutrino has a lepton number of -1. Let's put those negatives in brackets. So we have a total of 0 on both sides. So lepton number is conserved. We can also look at quark flavors. So let's rewrite the equation. The neutron is up, down, down, becomes a proton, up, up, down, plus the electron, not made of quarks, plus the electron antineutrino, again not made of quarks. So in terms of up quarks, we have 1 on the left, 2 on the right, and down quarks we have 2 on the left, becoming 1 on the right. So quark flavors not conserved. We should also identify which force or which fundamental interaction is involved, and there's lots of evidence here to tell us that it's the weak force. And we can give reasons such as the change of quark flavor. Let's just go back to the previous bit for a second. Clearly here what's happened is that a down quark has changed into an up quark. We started with 1 up and we ended up with 2. We started with 2 downs and ended up with 1. So the first sign that we've got that this is the weak interaction is the change of quark flavor, and also the presence of neutrinos. Always a good sign. Whether it's a neutrino or an antineutrino doesn't matter. If we see neutrinos, then we know that it's the weak interaction. So there, basically, we've covered everything that we need to for this particular question. We've identified the beta decay, we've identified the particles in a reaction, we've shown how the three conservation laws have applied: charge, baryon number and lepton number. We looked at quark flavours and found that quark flavours weren't conserved, and that, along with the presence of the neutrino in the interaction, told us that it was the weak force involved. Thank you very much for listening. Please remember to like and subscribe. Feel free to leave any comments. Goodbye.